Welcome to Physics Tips for Cambridge Students YouTube channel. Today we are going to be looking at systematic errors and random errors. This is the AS level physics in the 9702 syllabus. Now before we go any further, please make sure that you've subscribed to the Physics Tips for Cambridge Students YouTube channel and hit the bell notification so that you get notified of my future videos. Without much further ado, let's get started. Now, when we look at errors, that is systematic and random errors, please do make sure that you watched my video on errors and uncertainties. So these errors can be classified into two, that is systematic and random errors. Right, so when you do the experiment, there is always a true value that you want to find. For example, you want to get the true value of g, the acceleration of free fall. So suppose the true value of g is 9.81 meters per second squared. Now then you get values that are very close to one another and very far away from 9.81 meters per second squared. We say that there is a random error in the readings. Okay, there'll be random error in the readings. And then you happen to find values that have a constant deviation from the true value, These have what is called systematic errors. So we are going to start off by looking at systematic errors. So like I said, in systematic errors, the values do have a constant deviation from the true value. As you can see, the true value is right at the center of the circle, and then you tend to have values scattered on one position, that is they have a constant deviation from the true value which is at the center. We say that there is a presence of a systematic error. Okay, so a systematic error is then defined as an error which arises when the values have got a consistent deviation from a true value. Examples of systematic errors are zero errors. That's the most common example of systematic error. So for example, we've got if we have a voltmeter or an ammeter, the voltmeter and ammeter should be adjusted to read 0 before use. If there is a constant, like if it's not starting from 0, it's starting maybe from 0.5, 0.05, something like that, then you need to record the error as well, and then you subtract the error or you add the error. Remember, when you talked about these errors, they could be positive or negative. Positive 0 errors should be subtracted from values. Negative 0 errors should be added back to the values. Okay, so positive you subtract, negative 0 errors you add back to the readings. Now we also have poor experimental technique. For example, if someone has a constant parallax error, like you are reading from the same point, you say you have got a ruler, and then you are reading from above the ruler instead of reading perpendicular to the reading. So say your eye is because your eye is supposed to be perpendicular, and then you're constantly reading from an angle above, then your values tend to have a parallax error. So that parallax error is a systematic error. But then if you are constantly shifting the way you are viewing the reading, say from top to bottom, that parallax error becomes a random error. Okay, so parallax error can either be random or systematic. So systematic in the sense that you are viewing from the same point or same position all the time, but random in the sense that you can change the way you are viewing the reading. So that is a parallax error. Also, misreading a scale results in a systematic error. When reading the position of the pointer on a scale, the eye should be placed directly over the pointer to get a correct reading. So you've got to have your eyes perpendicular to the scale reading. If for this case of measuring cylinder, for the case of an ammeter, remember it is like curved like this, so your eyes should be directly above the readings so that you get true reading. Many ammeters and voltmeters have more than one scale, e.g. the 0 to 5 and then 0 to 10. The 0 to 5 may be inside, and then we've got the 0 to 10 on the outside. Now if you use the wrong scale, say you are reading 6 volts and then you read it as 1 volt because 1 volt corresponds to 6 volts times, then you tend to have a systematic error. So you're using the wrong scale altogether on the same instrument, so that results in a systematic error. Then you have what are called inherent errors, e.g. heat losses. Say you are in an environment where there is that constant heat that is given off to the surrounding because of the difference between the room temperature and the experiment. So there's always that heat loss to the surroundings which is constant due to that environment where you're doing the experiment. So that is a systematic error. Also air resistance. You're performing an experiment where there's air resistance. That air resistance is a constant for that particular environment. That also is a systematic error. Also remember, when you're dealing with atomic physics or radioactivity, there is always that background count when you want to use the Geiger-Müller tube to find the activity. Okay, so you tend to have a background count which is fluctuating, of course, around a certain value. Then that value, you need to find the average of it, then that becomes the background, and then you subtract from the background reading from your readings always, because that is a systematic error. To account for heat losses in heat experiments, the experiment can be repeated with a different rate of heating or cooling. Correction may be applied. Okay, so you need to change the conditions, and then you get new parameters. Perhaps you could use some what you call a system of simultaneous equations to eliminate the heat loss, and then you can work out the whatever you're working out, whether the heat or the specific heat capacity. Now draft shields may be used to minimize air resistance as well. In radioactivity experiments, the background count is measured and subtracted from all measurements to get a count rate due to the source alone. When measuring the magnetic field inside the solenoid due to a current, the background field is first measured without the current, and then you always subtract it. Systematic errors cannot be eliminated by taking repeated measurements, okay, or by averaging. They can be eliminated or corrected by changing the equipment or the instruments that you are using or using a different experimental technique or experimental procedure. Then also adjusting the readings to compensate for the systematic error. Now suppose a zero error is the only systematic error that is there, then you can eliminate the systematic error by simply subtracting it or adding it back to the readings. Now let's move on to random errors. Now for random errors, you tend to have the values scattered about the true value. Okay, so you tend to have values scattered about the true value. As you can see, we have the true value at the center, and then the values are scattered around the true value. So if you take an average of all these readings, you may get that true value over there. So in random errors, they result in a scatter of readings about a mean value. Random errors are due to the experimenter taking readings incorrectly or random fluctuations in the environment affecting the experiment. Some of the causes include inability of the observer to repeat his actions precisely, like I gave the example of the measuring cylinder. When you are viewing from different angles, then you are not viewing from the same angle, so you tend to have a random error in there. A particular measurement not being reproducible, right? So you are doing the experiment, you want to redo the experiment. Say you want to find the value of R when I is equal to 5 amps. So in that case, you then get in V is equal to, say, V is equal to 12. So you try to adjust to get V, then you get a value of 11 point something at the first place, you get 10 point something for the second case. So your values of R would tend to fluctuate. So we can say that the reproducibility of the reading is very, very hard. So this then reduces the reliability of the results. So again, if in timing the period of a pendulum, the reaction time on the clock might vary slightly. You may be too quick on one measurement and then too slow on the other for the same starting amplitude. Then you tend to have different times. So that's again the issue of reproducibility there, where you cannot repeat the actions precisely. Also, when a value measurement cannot be reproducible, that is when measuring the temperature for plotting a cooling curve, you may not reach the actual temperature that you started off with or that you once reached. Then lack of sensitivity of the instrument. So suppose you use a ruler which has markings from 0, 0.5, then 1, 1.5, 2, 2.5, etc., etc. And then someone uses a ruler which has 0, 1, 2, 3, 0.1, 0.2, 0.3, 0.4, 0.5. So you see this is more sensitive than that one. So you tend to estimate a value that is between 0 and 0.5. So you will not estimate with accuracy. At times you tend to say a value that is there is 0.2 and someone says 0.3. So then you tend to have a random error there. So also, like when using a micrometer to measure the diameter of a wire, it gives a smaller percentage error than using a vernier, because a micrometer is more sensitive than a vernier calipers. Then random errors are reduced by repeating. Okay, so like I said at the beginning when I talked about these random errors, if you add those values and divide by the number, you tend to reduce the random error. You cannot entirely eliminate random errors, but you can entirely eliminate systematic errors. Like I said, if the systematic error is purely a zero error, then you can easily subtract the zero error. If it's a positive zero error throughout, then you have eliminated. But for random errors, if you find the average, we still have that probability of an error occurring. Right, so we're going to look at this example and then we end this video so that we keep it short. Suppose the readings of the diameter of a wire using micrometer screw gauge are 0.83 millimeters, 0.83 millimeters, 0.85 millimeters, 0.83 millimeters, 0.85, and 0.86 and 0.85 again. So you're supposed to calculate the diameter and state the uncertainty in the measurement. Now in the AS practicals, that's what you're going to meet up with. Okay, so you are asked to find the diameter, and with its uncertainty, what you need to do is to measure the diameter spirally. So you have got a wire there. So you take the diameter on different places, let's say from this, and then from to that, to that, to that, and then to there. Then you also will be turning the wire so that you also take into consideration the non-uniformities on the diameter of the wire. So if you do that, then you get these readings that they've given you over there. Right, so now you tend to find the average afterwards. So after finding the average, say you add the values, then divide by the number. So I'm going to look at the answer there. So you tend to add the value. So the mean will be the addition of the values divided by 7. You get 0.843. Then you look at each of the values, its deviation from the mean value, the deviation of this one from the mean value, deviation of this from the mean value, and so forth and so on, all the 7. Okay, so these have been given here as 0.013. So in other words, we're saying 0.843 minus 0.83, 0.843 minus 0.83, 0.885 minus 0.843. You always take the bigger one to subtract the smaller one of the two. So you should neglect the sign. That's what I said there. So once you've done that, you add those. These are deviations, which could be errors. Then you add those, divide by the number, which is 7, and you get the uncertainty in the measurement. So it comes to be 0.011. Remember, we said absolute uncertainties are expressed to 1 SF, so which means the value now becomes 0.84 plus or minus 0.01. Remember, the value then would need to be expressed to be consistent with the decimal places on the uncertainty. So it becomes, instead of 0.843, it now becomes 0.84 plus or minus 0.01. Okay. Then lastly, I want to talk about accuracy and precision. An accurate experiment of low precision tends to have the values all scattered about the true value. So the value will have a small systematic error, okay, and a large. So in this case, we've got a large random error and a small systematic error. So if you have the values, they form a scatter of points that are very close to the true value, but then scattered. So which means there's a large random error, like I showed the picture that I showed, that there was a very large random error there. Let me go back to that. So there's a large random error, but they are scattered around the mean value in the middle. Okay. Then we tend to have values that are precise but less accurate. In other words, the true value is this one. The values are scattered on there, which means they are far away from the true value. So there is a very small random error in terms of the scatter of points. As you can see, the scatter is very small, but then we've got a large systematic error because the mean of those values is far away from the true value itself. So it is possible to have readings which are accurate but not very precise, or readings which are taken with great precision which are not accurate. So precision refers to the random error. So high precision means a very small random error. High accuracy means very small systematic error. So an accurate experiment is one in which there is a relatively small systematic error. A precise experiment is one that has a small random error. So a precise reading is a measure of the smallest measurement that can be made with an instrument. So for a micrometer, the values taken by a micrometer will have a precision of 0.01 millimeters. And then vernier caliper 0.1 millimeters. Then meter rule 1 millimeter, but that's plus or minus. And then the protractor, always you state your values correct to the nearest degree. All measurements should reflect the precision of the instrument used when you're doing your practicals. E.g., 3.30 millimeters means that someone has been using a micrometer. Okay, if you say 3.3 millimeters, then it means that you have been using a vernier calipers. So when the examiner knows that the instrument that was supposed to be used there was a micrometer, you lose a mark because you have used the wrong, for expressing your measurement, you have used the wrong precision. Okay, similarly, we have 25.5 centimeters for a meter rule because the smallest division that it can measure is a millimeter, and there are 10 millimeters in a centimeter. So that when you want to express your readings in meters, you have got to have 3 decimal places because there are 1,000 millimeters in a meter. I think my video should end here so that I keep it as short as possible. I hope you have found use in this, and please let me know in the comments, and do not forget to subscribe to the channel, and so that you get notified of future videos. If you can also share these videos among other students that you think could be that could benefit from this. Signing out.